Welcome to this electronic presentation. My name is Lefeber. I'm from the robotics group of the VUB and I initiated this research on prosthetic devices more than 12 years ago. In this presentation, I want to give you an overview of our design approaches. The presentation is based on the research work of Joost Gerons, Louis Flynn and Pierre Cherel. At the end of 2019, this research led to the creation of a spin-off called IROS2020. The spin-off aims at bringing our transtibial prosthesis from a research status to a market product. Walking with our current state-of-the-art prosthetic feet feels like walking in loose sand, or as walking with closed ski boots. Most prostheses are passive devices, just as they were 50 years ago. They hardly adapt to the environment, they do not assist you during walking or going up or downhill, mostly because there is no or a limited ankle rotation. People have to walk step by step instead of step over step. In consequence, the rest of the body of the amputee needs to compensate for this, and this can lead to physical problems at knee and hip. We have the goal of allowing people to walk as normally as possible, meaning we would like to reproduce the full biological sagittal plane torque and kinematics. This graph gives the torque angle characteristic of the ankle. We start at initial contact with the heel strike and go to foot flat without creating a torque. But from that moment on, till the heel off phase, our muscles produce a very high torque, 120 Newton meters for a person of 75 kilograms. This torque is used to do a push-off from the heel off till the toe off phase. On the top graph you can see a 300 watt power burst during this push-off phase. In conclusion, we need a very high torque and very high power. Technically this means a huge motor, but the weight of that is a problem with that. If you put weight at your ankle, it becomes very difficult to walk with that. So we started to look for solutions to produce this high torque and high power with an actuator as small as possible. For that we studied the effect of adding a parallel elastic element that could restore part of the torque and the energy required to walk. There are different possibilities. In the middle graph we placed a passive spring near the initial contact. You can see that the remaining torque, the long green dotted line, is already significantly lower. One can play around with this spring and place, for example, the passive element more in the middle. Now we have even negative torques, but certainly lower torques than the original ones. For most of our ankle designs, we used to design in the middle, mainly because during normal stance, no motor torque is needed. Based on these principles, we developed different working proof of concepts of the so-called ankle mimicking prosthetic foot, starting with a fully passive design, then active, with first a single clutch, then a double resettable clutch used for self-adaptation to slopes. The achieved innovation is a new bionic foot. In the video you see a passive version that adapts naturally to slopes. Now our spin-off IROS2020 works hard to bring the next generation of bionic prostheses to the market and to improve the quality of life of amputees. In 2012, we became a partner in the European CYBERLEGS project. In 2017, this project was extended to the CYBERLEGS++ project. The main goal of our part of the project was to develop a device that would allow a person who has suffered from an amputation to regain the ability to walk efficiently with little user effort. Ideally, this would help patients with an impaired contralateral limb, such as weakness due to age, diabetes, or any other secondary complications. The device would ideally also assist in rehabilitations. Improvements in the rehabilitation could have benefits in terms of actual use of powered prosthetic devices. A secondary goal of the prosthesis is to assist in high-powered tasks, such as sit-to-stand and stair climbing, tasks that are quite difficult for weaker individuals to perform. Although we had different design for our ankle-foot prosthesis, the same quasi-stiffness approach as for the am-foot was followed, so I will not go in more detail on the ankle design. Next, we present the knee actuator and how it progressed from an essentially passive device to a fully active device incorporating the passive characteristics that were initially developed. On the left side of the slide, you see a typical torque angle graph of the knee during average walking. Here we split up the knee behavior into 3 different periods. The weight acceptance, which is a period of stance flexion directly after heel strike. An energy transfer period, which is a period defined by an extension torque in late stance with increasing knee angle. And a swing extension phase, which is the knee extension that is done to get ready for the next heel strike. Weight acceptance and energy transfer will be explained in detail in the next slides. We showed it was theoretically possible to recreate the knee flexion extension torques properly using the semi-passive locking mechanisms of the alpha prosthesis. And we wanted to incorporate those principles in an active design capable of providing extra torque for actions such as sit-to-stands and stair climbing. This was done through the addition of a so-called slide carriage series elastic actuator, where the spring providing the baseline torque was used as the series spring for flexion torques. The system was left relatively untouched for the gamma prosthesis, although the actuator motor and gearbox were changed to gain a bit more power for additional velocity and torque. Looking again to the knee torque angle characteristics, we also see immediately that there is a period of time during the gait that looks very spring-like. We call this the weight acceptance phase, providing a period of flexion and extension right after the heel strike, in green on the figure on the left. We emulate this behavior using what we call the weight acceptance system, which uses a small motor to place a spring behind the knee during this portion of the gait cycle. After this period, the motor removes the spring out of the system, allowing for uninhibited knee flexion for the rest of the gait cycle. This is what happens during the energy transfer period of the gait cycle, shown in the torque angle graph on the left. We kinematically link the knee and ankle, and as the knee flexes, the energy stored in the baseline spring and the knee energy during late stance flexion is transferred to the ankle. The alpha prosthesis used a single tooth ratchet to lock a pulley and pull a cable that was routed down the back of the prosthesis to the rear of the ankle. This meant that the timing between the knee and the ankle could not be actively controlled and was set to a specific knee angle. We attempted to address this using a cable that could be adjusted in length by adjusting the position of a pulley on the rear of the beta prosthesis. If the pulley was down, the energy transfer mechanism was effectively unlocked. Raising the pulley with a motor changed the angle at which the knee actuator would pull the ankle. On the bench tests, the energy transfer mechanism worked as expected, and energy was able to be saved during the gait cycle, as well as a transfer of torque from the knee to the ankle. But getting the timing correct proved to be difficult. Out of hundreds of strides with the alpha prosthesis, only a handful actually had actual measurable energy transfer from the knee to the ankle. In this case, the resulting transfer was considerably lower than what was tested on the bench. We never made specialized controllers to monitor the energy transfer system and detect what strides would be suitable to engage the system, which might have made the system more reliable. Also, on the bench, the weight acceptance mechanism worked well, saving energy from the gate cycle as expected. But in practice, the weight acceptance wasn't really used by the amputee. Over the course of both CYBERLEGS projects, we were able to build 3 totally new devices that allowed us to reproduce the biological knee and ankle torque angle characteristics of average walking data in a variety of ways. Sadly, not all the things we did turned out completely positive, although we did show that the behavior of our ankle was about what we had expected and produced positive joint work as was designed. Positive was that the prosthesis was able also to be used for other tasks, such as sit-to-stand and climbing stairs step over step. Not only our prostheses were used in the lab. In 2016, we were able to go with our beta prosthesis to the Cybathlon event in Zurich to perform tasks such as hurdle navigation, which were never considered during the initial design phase. The video that is playing shows the behavior of the device on a treadmill, as well as a number of tasks that were completed in the Cybathlon contest. We also show how our subject would complete the same task with his standard C-leg prosthesis. To further study these devices, we needed to simplify the system, and in fact we developed a new architecture, the CYBERLEGS X-Leg. The CYBERLEGS X-Leg is a complete relook at all the collective issues we had with the previous CYBERLEGS prosthesis, and we addressed them through a highly simplified and fully self-contained device. The energy transfer system and the weight acceptance systems were removed, as such reducing the required number of sensors, components and motor drivers. The knee angle is increased, which is necessary for better sit-to-stand capabilities, and the modular design is used, which was never considered in the past due to the desire to have the energy transfer mechanism. The modular design will also increase the ability to focus on specific aspects of design and control without the influence of other joint behaviors. Motor drivers are now situated in each module. Batteries and controller are contained entirely in the knee. This device will allow us to better focus on issues such as sit-to-stand, and especially allow us to refocus on the elderly population who has specific needs that are not necessarily covered by average walking data and were not addressed specifically in the previous designs. Ultimately, would like to get this device to a specific group of people who can use it for extended trials and allow us to focus on developing better control for active prosthetic systems. Thank you for your attention.